things, geology. And I hope it's becoming one of your favorite things too. I mean, it's a fascinating science dealing with the age of the Earth at 4.6 billion years and everything that comes thereafter. So let's take just a couple minutes to review where we were and make sure that you've got your mind around that. So on the screen, you can see the geologic timetable. And what we said is that we are first describing it relatively. So we're looking at it in terms of a sequence of events that have happened from oldest at the bottom to youngest at the top. So our oldest unit of time that we've described is the Precambrian. The Precambrian is an eon. And the Precambrian starts at 4.6 billion years and goes to 570 million years. After that, we are in the Paleozoic. The Paleozoic is followed by the Mesozoic and the Cenozoic. Paleo means ancient, Meso means middle, Ceno means early life. The Paleozoic, Mesozoic, and Cenozoic are separated by mass extinctions. And then we can talk about how each of those different geologic eras are broken up into geologic periods. And we said there was a mnemonic for you to help organize that in your minds. Come over someday, maybe play poker, 3 jacks can take queen, and that helps us to describe the Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian, Triassic, Jurassic, Cretaceous, Tertiary, and Quaternary. So putting those into relative time, oldest to youngest. We said that those geologic periods are separated by the uprising of life as described by the fossil record. And we use the Devonian as an example. So Devonian is often called the age of fishes. And then we said that the Cenozoic is broken up into the Tertiary and Quaternary, and it's also broken up into different geologic epochs. And those epochs are described by climate change. So we have a really good record of climate change over the past 66 million years to modern day. When we describe modern time, it depends on the detail that we need. So we can describe modern time as the Cenozoic era, the Quaternary, or either the Holocene or Anthropocene. There's a new geologic epoch recently that's been added called the Anthropocene that describes climate change and that describes how our human contributions of carbon dioxide have ramped up temperature since the Industrial Revolution. So that's our geologic timetable. We also describe the idea of geologic gap. So if the cat is white, does that mean the cat has never been peaked? And that's just the idea of filling in different parts of the geologic timetable without making assumptions. We used the T-Rex as an example. So we thought that T-Rex was the biggest and baddest land predator up until 2019 when the Gigantosaurus was described. So that's one of the things that makes geology so exciting is that we're constantly learning. And I don't think I mentioned this last time, but when we talk about the fossil record, only 10% of life on the planet usually makes it to becoming a fossil. So it's really hard to become a fossil, and then sometimes changes in the landscape make it very hard to find those fossils. So filling in those records are really exciting for us in the world of geology. And then we talked about the idea of geologic boundary, and usually geologic boundaries are relating to overcoming technology. So we said the mass spectrometer helped us to overcome a geologic boundary where we weren't able to identify the age of rocks prior to 1950. And then once we were able to, the science kind of took off and soared, and it really put pieces of the puzzle together. Being able to go to the bottom of the Marianas Trench drastically pushed us forward in geology, but also in the field of biology, where we're able to learn what is exactly living at the bottom of the Marianas Trench, 28,000 feet deep, gives us different clues. And of course, like we can talk about going to Mars as being overcoming a geologic boundary or technological boundary that would be really exciting, where we learn as a scientific community as a whole. So I hope from that last lecture you've kind of got grounded in geologic time, and it's going to be a tool that we keep coming back to as we move forward in the class. And particularly today, what I wanted to focus on is the idea of rate. So in geology, we're not just interested in time, but we're also interested in how quickly things change. That's a commonality that we might have with like chemistry, where you're measuring rates of change, or even in biology. And so my first question to you then is, how fast is fast? What's the fastest thing that you can think of? Because this, just like asking questions of age, kind of puts it into perspective for us in our human lifetime, what we're dealing with here. So how fast is fast? My brother would say that GSX is fast. My other brother would say that the Blue Angels are fast, the F-18 Hornets with a maximum speed of over 2,000 kilometers per hour. I'm from Detroit. I think you know that. So anytime we talk about super sport cars, we consider those to be fast. But all kidding aside, we are looking to establish rates on the planet. So when we talked about the oldest things on the planet that were alive, we mentioned like the redwood trees as one of those examples. And so the redwood trees, upwards of 500 years old. But as they grow, they're only growing like 1 centimeter per year. So they have this very slow and steady growth rate that we can truly appreciate in the world of biology. But when we make comparisons between the rate of which a tree is growing to something bigger than that, so a process that's bigger, and maybe we're thinking in terms of plate tectonics, it helps us to put it into perspective. So as an example, we can ask the question, how quickly are mountains uplifted, or how quickly are mountains eroded? So the Himalayan mountains, for example, are being uplifted at about 1 centimeter per year. So what we're going to learn is that there's something called a convergent plate boundary that's forcing the uplift of the Himalayan mountains at about 1 centimeter per year. So in terms of geology, that's really fast. If we look at Iceland, a place that is near and dear to my heart, Iceland is being torn apart at about 2 centimeters per year, or 13 miles per million years. So if you add up all those tiny movement every year over a million-year scale, it's significant. And that's really what we're trying to get our mind around here, is that rates that appear on the globe in a human lifetime that are slow are really significant over geologic time. So when we establish rates, we're looking at two different types. We're asking questions about linear rates and nonlinear rates. So my question to my viewers at home, are linear rates commonly found in nature? What's a linear rate? So you remember that you have an x-axis, and then you have a y-axis, and you're either looking for an increasing or a decreasing trend. Is a linear rate. So you're looking for an increasing or decreasing rate. So an example of a linear rate might be college tuition. Increasing. Do you get it? Yeah, I know you laughed. Thank you for that. But our question is, are linear rates commonly found in nature? And your answer is no, it's not likely, because there's a whole lot of different variables. It is not natural for something to continually increase. So instead, we look for all different types of nonlinear rates. Changes not constant. These are most often found in nature. What are some examples of nonlinear rates? So we can think in terms of a bell-shaped curve. We can think in terms of an exponential curve. We can think of rates that increase and decrease, so maybe even like an oscillatory type of curve. So when we think of nonlinear rates, a scatter plot would be another example. There's many examples. So for a bell-shaped curve, you might think in terms of maybe a rainfall event. So where you have rain falling over an area, it reaches its maximum point of precipitation and then decreases. Oftentimes we look at river systems when we're monitoring water, and that's called a hydrograph. So you're looking at the discharge of a river over time. We can look at an oscillatory curve. So often animal populations are mapped like this, predator-prey relationships. So if you have an increase in coyote population, you often have a decrease in maybe bunnies because that's their food source. So an oscillatory relationship. And then exponential decay curves or exponential growth curves in terms of population. So the population of the planet is continuing to exponentially increase over time. So rates give us a mechanism of which to describe changes that are occurring over the planet. And for me, and my particular science as a tsunami scientist, I'm particularly interested in finding out how frequently these events occur over time. And a frequency then is a measure of how often an event occurs. How frequent is frequent? So in college, I used to call home and say, I go to the library frequently, Mom and Dad. No, it was true. I did. I was a very good student. Still am. So establishing a rate of how frequently something happens. Again, so tsunamis, they do not occur frequently, but we want to establish a rate so that we can describe that natural hazard or natural disaster. And my big brothers always say, you know, you got to keep it real for these students. So here's a question for you about frequency. How many times has University of Alabama beat University of Georgia? I'm sure somebody cares about the SEC out there. And the answer is 35 out of 60 times. But go Dogs. I don't like football at all, so it doesn't really matter. Okay. Back to frequency. A measure of how often an event occurs. We use a tool that's called a recurrence interval to measure this. By definition, a recurrence interval is used to estimate the risk of an event to occur. So go ahead and write this down. Ri equals n plus 1 over m, where n is the number of years of data and m is the magnitude of the event. So the largest event on record will be described as a magnitude of 1. And you might have heard the term magnitude, right, when describing earthquakes. And that's exactly a natural disaster that might be used to describe a frequency of events. So a recurrence interval, n plus 1 over m. And so let's go ahead and practice. Assuming there is 99 years of data, so n is 99 years, how frequent will a large magnitude 1 event occur? So in this case, you take 99 years of data plus 1 and you divide it by 1. So you're going to end up with 100 years. And so what that 100 years means is the largest flood on record is expected to occur once every 100 years. What I need you to recognize too, when we look at this equation and talk about the number of years of data, is that n is called the limiting factor. So your data set or your event that you're trying to describe is only going to be as good as the number of years of data that you have. So for example, for most of our data sets in the United States tied to climate or rainfall only goes back about 150 years. 150 years is kind of pushing it, but we'll say at best 150 years. In Rome, Georgia, we have rainfall data that goes back to 1866 as an example. So our data in predicting the 100-year flood, the 500-year flood, is only as good as that data set. In Japan, for example, if we're talking about tsunamis, Japan in their temples goes back about 500 years. So they have these beautiful temples. There's somebody who has always lived at the temples, and they describe events that occur. So we might not know the size of a tsunami, or we might not know the intensity of the earthquake, but from their descriptions, we can make some estimates. So, so we are reliant upon the data that we have, and then from there we can make like computer modeling as such. So back to our question here, assuming there's 99 years of data, how frequent will a large flood occur? 99 plus 1 divided by 1 is 100. And what is this saying? The largest flood on record is expected to occur once every 100 years. Which leads us to our second question. Does that mean a 100-year flood can't happen twice in a year? Does that mean a 100-year flood can't happen twice in 1 year? And your answer, of course, is no. But the probability or the chance of 100-year flood happening twice is less than 1%. And so there's a equation that we can use to determine probability. So probability is recorded to you in a percent. So it is 1 over the recurrence interval, and then you multiply that by 100%. So 1 over recurrence interval multiplied by 100% is how we calculate probability. And probability is used to estimate the percentage of an event to occur each year. So how likely you expect it to occur. So we talk about the 100-year flood. The 100-year flood should happen once every 100 years, but the probability of it happening twice in 1 year is less than 1% chance. It can happen, but it's unlikely to happen. And probability is important for you as a citizen, because if you're in the business of buying a house and you have to have an insurance agent come out to insure your house, they're likely going to talk to you about the percentage of your house flooding, or if you're moving in California, the percentage of your house being in an earthquake zone, so the likelihood of that destruction. This is a map of the city of Rome, Georgia, and what's highlighted in yellow is the areas that anticipate flooding if and when a 100-year flood would occur. So what you're noticing is that in the city of Rome, there are 2 river systems that ooze down at one river, and they converge in our downtown area to form the Coosa River. The Coosa River flows to Alabama, of course. And so you notice that a lot of the downtown area is built in the floodplain. So the floodplain is the area that's adjacent to these river systems. And in the city of Rome, that was established in the 1800s, it made a lot of sense because they used the rivers for transport of cotton. So our city center is built around the idea of utilizing these river systems. In 1886, there was what was thought to be the 100-year flood. So if you're downtown on 3rd Avenue in Broad Street, Rome, Georgia, by the Rome History Museum, there is a marker that establishes April 1st, 1886, and this is the high water mark. And what you see on there is it says that the flood stage is 15.29 feet above the flood stage. And so what that means is the top of the riverbank was full, and there was an additional 15 feet of water on top of it. So the channel itself holds about 30 feet of water, and there's an additional 15 feet on top of that. And when we look at historic pictures of the downtown area, you see these types of things that are recorded. So you see people that are have their canoes and they're out on Broad Street. So let's take a look at the data real quick. So on the x-axis, you see time, And on the y-axis, you see annual peak stream flow. And this is also called discharge, and it's in cubic feet per second. So how quickly the water is moving past a point. And this data takes us up to about 2015. So about 5 or 6 years ago. What you'll notice on the very left is the 1886 flood up here at 70,000 cubic feet per second. So the volume of water that was anticipated flowing past the Untitled River on downtown Broad Street when there was 15 feet of additional water sitting on top of the road was about 70,000 cubic feet per second. If we were to take an average of this, we would see that typically you don't see high water events that are above 20,000 cubic feet per second. So this would be considered the 100-year flood. If you do the math, 1886, 100 years later, is 1986, and so we're past due for a 100-year flood based on this data. What has happened since then is that the city of Rome has put in levees. And so oftentimes when people live on a floodplain, they put in these structures that are called levees. And a levee is essentially built of earth and gravel and their mounds to protect an area for flooding. So the water would have to go up and over the levee in order to go into the street. So when we looked at that initial flood map, what we found was that the majority of our downtown areas would have been in the flood zone. And so in the 70s, these levees were built. Here's an aerial photograph of the downtown area. This was from 2019. And what you're seeing is a view of the Etowah River. Here's Barron Stadium. Here is the major road going towards campus. And so what you're noticing here is that the flood stage was nearing the breach of the levee. So the levee is this brown, the green area over here to the right, and you can see how close we were even during this flood event to exceed the capacity of which those levees are built. So the good news is we do have those levees in place. The bad news is that we're likely up against a 100-year flood. The other good news is that we are able to regulate the amount of water flowing downstream of the Etowah River by the reservoir called Lake Allatoona, which is upstream. So there are some preventions in place, but when we look at the anticipated amount of water from the 1886 flood, and we make those comparisons to what we have seen over the past 100 plus years, it's significantly more. So prior to, so if 1886 is our highest flood event recorded, you'll notice in the 40s, we've approached about 50,000 cubic feet per second. And the flood that happened in 2019, or the picture I just showed you, was only about 40,000 cubic feet per second. So it's interesting and important to study recurrence intervals so that we have an idea of when we think the next flood event should occur, and we can anticipate how much water we think might be present, so that we can evacuate and try to curb the problems that will follow. So making a comparison in recurrence intervals to probability, what you need to realize is that when you have a high recurrence interval, there's always going to be a lesser probability of a chance for it to happen every year. So the likelihood of a 100-year flood happening every single year is less than 1%. However, when we have a recurrence interval of 50 years, there's a 2% chance. Recurrence interval of a 10-year flood, the probability is 10%. So a question that I often get is, when we're figuring out magnitude of events in recurrence interval, the number of years of data doesn't change. So we said 99 years of data plus 1 divided by 1 would be your 100-year flood. If we have 99 years of data plus 1 and we want to find a magnitude of 2 event, so magnitude 2 is a smaller event than magnitude 1, we divide and we get a lesser recurrence interval. We get a recurrence interval closer to 50 years. So the probability of it happening would increase because it's a smaller event. So with frequency, one of the things that we're trying to determine is if the change is repeating. So if you see the event happen often or not. And an example of a type of change that is non-repeating is like going from childhood to adult. So again, we're thinking about things in nature that are not repeating, but more likely there are many things that are repeating. So what type of change that can occur that's repeating? The sun rising, the sun setting, the tides coming in, tides coming out, seasonality. And then with frequency, we also like to describe things that are periodic versus episodic. So if it's periodic, it's happening on a schedule, like the sun rising and the sun setting and the tides. If it's episodic, it is likely to occur, but it doesn't occur on schedule. So something like a mass extinction happens episodically. And we do all of this frequency of change and recurrence intervals because it's our goal in geology to identify if events are catastrophic events or if they're non-catastrophic events. So a lot of what my science does is we gather this information for the purposes of developing hazard mitigation maps or like giving this information to things like to flood insurance. My research in Puget Sound, looking at tsunami deposits, the idea was we wanted to establish if there had ever been tsunamis in this particular area so that we could make some predictions as to if there would likely be another one, and if there was, how many people would be in danger. So in Washington State, there's 2 major fault zones. There's one in Seattle, there's one in Tacoma. Those are both cities with millions of people. Earthquakes generate tsunamis when they are coastal or if there's a major body of water, as in the case of Puget Sound. So it's important to have an understanding of what your natural environment is in case these disasters happen and to make some sort of prediction so that we can raise awareness and teach people warning signs and how to deal with those events. So how is a catastrophic event different from a non-catastrophic event? In geology, we look at the destruction of the landscape, which is a little bit different than how other sciences view catastrophic events. So really, a catastrophic event is one that is going to have economic losses primarily, and then the second is going to be the loss of lives. So the most catastrophic event that has happened in modern time would be the 2006 Indonesia tsunami event that happened in the Indian Ocean. And so it fits into all these categories. It had drastic changes in landscape. It killed about 300,000 people within 2 hours. So we had major loss of lives, and its economic loss was devastating, and it was the largest, most economic loss from a natural disaster until Hurricane Katrina happened. So Hurricane Katrina lost less lives, but the economic damage to the area of New Orleans and the Gulf Coast was much higher. Mostly because when we talk about the Indian Ocean tsunami, most of those places were heavily populated, but they were developing countries, undeveloped or developing countries. So thinking in terms of Indonesia, Thailand, etc. So Catastrophic versus non-catastrophic events. A catastrophic event is going to be one that has a high magnitude. Write this down. A catastrophic event is one that has a high magnitude and a low recurrence interval. So a low frequency as a result. So a 100-year flood event is considered to be a catastrophic event. It has a high magnitude, which means it has, if we're talking in terms of flooding, it's going to have a high discharge, versus a non-catastrophic event would be like a rainfall event. So small amounts of precipitation that doesn't really make a difference or impact lives. So catastrophic versus non-catastrophic events. And we like to do this in geology because there was something that was called the catastrophic viewpoint. And it's really where the basis of our science formed was on the catastrophic viewpoint. So I mentioned that it wasn't until 1865 that we had a geology textbook. And so describing geology prior to that had to do with the catastrophic viewpoint, and not just really in geology, but in all of science. The idea that the Earth was only about 6,000 years old, and some people still hold this view today. It's still called the catastrophic viewpoint. The view that the Earth is only 6,000 years old, and so when we look at the formation of things on the planet, that means that they have to occur catastrophically. So when we look at the mountains or volcanoes, the catastrophic viewpoint holds the idea that these things were built very quickly. And it wasn't until the 1800s when James Hutton comes along and he describes a paradigm shift, or initiates a paradigm shift, suggesting that the formation of the Earth is probably older than 6,000 years. So he's kind of looking at natural processes and saying, I think the Earth is older than 6,000 years. And remember that good old Jimmy Hutton is having to use relative dating techniques, as we've already established. So looking at things in order of sequence to establish the idea that the Earth is probably older. So he puts this, publishes this idea, and it begins a paradigm shift. So what's a paradigm shift for my viewers at home? That's right. It's a shift in thinking. So this shift from a catastrophic viewpoint to a non-catastrophic viewpoint is initiated in the late 1800s. So here's good old Jimmy Hutton on the screen. Jimmy Hutton living 1726 to 1796, so right at the beginning of moving into the 1800s. He dies just before, and he introduces the idea of uniformitarianism. And uniformitarianism, in brief, means the present is the key to the past. The present is the key to the past. So identifying processes on the Earth's surface gives us an idea of what might have happened in the past. So Jim Hutton lived in England. He lived on a meandering river, so a river similar to maybe like the Etowah River. So a meandering river is one that has curves. And his house was built very close to the river. And his wife, Mrs. Hutton, goes to him one day and says, Jim, I think that river is coming closer to our house. You need to do something about it. And Jim's like, great, another thing I have to do. No, I don't know if he says that, but he's like, okay, so he goes and looks at the river, he looks at the house, and he takes what? Measurements. And he makes what? Observations. And he begins to write down rates of erosion. So he's writing down how quickly the river is moving towards his house. And his wife was right. His wife, she was right. She was right. The river was coming closer to his house. But the thing that Jim Hutton did, making observations and writing down rates of erosion, was a kind of like a new idea. And so he publishes that, and he presents this idea of uniform rates, which ends up being wrong. And the idea he presents is like the Earth is trying to achieve like a steady state. But this is going to be termed the Huttonian Revolution. So remembering why his ideas are wrong, the events occur at uniform rate, is because he was measuring over one season. There wasn't a catastrophic event that occurred. And what we know is that you can have increases and decreases in rainfall that change the level of the rivers, that change the rate of erosion. So that piece of it is not going to hold the test of time. But this idea that by looking at modern processes, we can make some predictions about what has happened over geologic time is going to be called the Huttonian Revolution. So the present is a key to the past, or uniformitarianism. And so he puts us out there, and there's a paradigm shift that starts to think of the Earth as being much older than 6,000 years without still able to identify how old it is, but just these processes take a much longer time. So it was like giving a new appreciation for the landscape. So almost as soon as Jimmy Hutton dies, another fellow comes online, and this is Chuck Lyell. So Charles Lyell, 1796 to 1875, and he is French. And Jim Hutton, he was a naturalist, so he appreciated the natural environment, but just like a lot of the founding people in the science of geology, he wasn't classically trained as a geologist, and that's because it's not until Chuck Lyell writes Principles of Geology does our science form. So he's a naturalist, he's making natural observations. Chuck Lyell comes along, he's a bit better spoken and better written, so he's classically trained as a lawyer, and he is lucky enough to be independently wealthy, and so he studies law and then he begins to travel. And through his travels, he's making some detailed observations about different landscapes, Mount Etna. He's looking at volcanoes and asking questions about catastrophic events. It erupts when he's there, so he's able to write down even how the landscape changes from his viewpoint. And then he's thinking in terms of what Jim Hutton is saying and buys into the idea that the Earth is probably older than 6,000 years. And so by Chuck Lyell publishing this book, he is really pushing forward the Huttonian Revolution and embracing this idea that the present is the key to the past. And what we're going to notice is that this non-catastrophic viewpoint, also called uniformitarianism, has some problems. So what are some problems or challenges with believing that the present is the key to the past? Well, it's a little bit limiting, isn't it? So first of all, what we do know, and what even Chuck Lyell talks about in his book, is that catastrophic events do occur, they just don't occur frequently. So the landscape is changing catastrophically, but also non-catastrophically. Catastrophic events can have quicker and much more devastating change to the landscape, for sure, but those small rates of erosion that we talked about, or those small rates of uplift of mountains that happen, can measure up over geologic time. So again, to review, we said Iceland is being pulled apart at about 2 centimeters per year. If we add that up, it works out to be about 13 miles per million years. So it's looking in terms of, so uniformitarianism, this non-catastrophic viewpoint, is being questioned because catastrophic events do occur, non-catastrophic events also occur. Number 2, some processes occur so slowly that they can't be observed. And this goes back to like the idea of mountain uplift. So prior to GPS, we really had no idea how quickly the Himalayas were being uplifted or how quickly Iceland was being torn apart. So looking at those flow rates makes a difference. Rates in nature are not typically uniform, so that kind of washes out, as I mentioned, Jim Hutton's idea of uniform rates, because we don't see those. We see nonlinear rates that occur over time. Conditions of the Earth's surface change. So if I were to tell you that 26,000 years ago, the great state of Ohio was covered in 2 kilometers worth of ice, you might be surprised. And that's because when we look at Ohio today, there is no ice that's present. So the condition on the Earth's surface had changed. Lucky enough, we understand how glaciers move and how they entrain sediment and how they leave a record in the geological landscape. So we have evidence that there was once glacial activity there. But because conditions on the Earth's surface change over time, the present can't just be a key to the past, because sometimes things on the surface change. So what we say now is the present is the key to the past, but the past is also a key to the present, especially if we're talking in terms of climate change, right? So we mentioned that geologic epochs are the result of different changes of climate on the planet, and we have evidence of those. And we'll talk about that in detail. So if you want to know something about modern day climate change, it's probably best to explore to see how the planet has changed in the past relating to carbon dioxide levels, methane levels, glaciers, etc. If I assume the steady state is always achieved, and what we know is that although we love to make computer models that achieve a steady state, this doesn't happen in nature, and that's because things are changing at a nonlinear rate. So these were some of the big problems with uniformitarianism as presented by Charles Lyell and the principles of geology, working off of that Huttonian revolution. So at modern day, when we discuss and describe geology, we're focusing on something that's called actualism. And so the idea that principles of nature have been uniform through time. And the principles of nature that we're referring to include gravity, laws of thermodynamics, etc. So the idea is when we're looking at 4.6 billion years of time, we're saying that there's always been gravity. There's always been laws of thermodynamics. And that's important because when we are looking at the record, we can make the assumption, for example, that water always flowed downhill. And so it lets us use analogies when we look at field situations and lab situations, that those things that are occurring in the past probably occurred similar to what we find at modern day. So again, the present is a key to the past, and the past is a key to the present. And so geology is considered to be a historical science. There's other sciences that are non-historical. And so when we look at time, that is really where we are grounded. So nothing that we usually talk about doesn't have to have or infer time. And so that's why when we started the class, we truly started with the geologic timetable as our foundation, because we have to know where we are in the geologic record to make those observations. So whether it has to do with fossil record, evolution, climate change, etc., we get very excited about all of those geologic eras and geologic periods and epochs. So I think I'm going to stop here for today. That was a doozy of a lecture. I hope you enjoyed it, and we will be back at you next time. Have a great day. Winners do more.